Good morning, everyone. Okay, welcome to our lecture. Okay, so before we get started, for those of you who haven't downloaded the data sheets from the Luminous, please do so now. Okay, so in Luminous, there are two main data sheets. One is the under lab material. Okay, let me share the screen here for you to have a look. Okay, so under lab material, microcontroller documentation, download the Freedom KL25Z and the other one KL25P8 and so on. So that is the first one is the data sheet that is specific to the board that we are working on, and the second one or the one below is the one that gives us a lot of details on the actual microcontroller itself. Okay, so I will be referencing these documents very regularly, starting from today's lecture. And these are documents you should have with you at all times, okay, while you are working on your board. Okay, so you have not downloaded them, please download them now. Okay. Okay, so let's get started with the lecture. Okay, so today's lecture is going to be a very interesting and quite engaging one, all right, because we're going to be understanding the basic idea of how to use this board, okay, how to write the proper software for it, and we are going to learn the proper process, okay, by introducing you to the GPIO. Okay, so the GPIO, of course, all of you know, you have used it extensively in your other Arduino Uno or other controllers. But in this lecture, I'm going to teach you the proper way of writing code to control a peripheral block, and you're also going to be implementing that in the lab as well. Okay, so in today's lecture, in all the lectures, I will also use that time to also brief you all about the lab, the activities, and what you need to achieve in that particular lab, okay, with some demo on my side. So that will give you the necessary background info, so you can actually start working on the lab, even if you're not your session is not there yet. All right, so let's get started. Okay, so everybody can see my screen.
Yeah, okay.
Okay, thank you. All right, so before we start with the slides, so just a few admin matters. So last Friday, all of you, all this project and hardware related stuff has been settled. So all of you should be right now in a project group. Okay, so those who registered in the Google form that you did not have a project, okay, either you all form your group yourself or I allocated you to some group. Okay, so all of you should be in a project group. If you are not in a project group still, please let me know. Okay, then I will allocate you to some group. Okay, all of your project kits have been collected. Okay, so all the necessary items have been issued to you. I think the only thing that I think the morning group we forgot to issue is the additional header pins. I think inside the project kit, the header pins, okay, the header pins were only issued for one board, okay, inside the project kit bag that you collected. Okay, so for those of you who do not have enough header pins, you can the next time when you come to the lab, okay, you can just collect them from the TA. Okay, so that is for you to solder onto the side of the board, okay, for all your connections. Okay, and each of you have been issued your own freedom board. Okay, so except for those who are still stuck overseas, all right, you have been issued. So some of you asked your friends to collect on your behalf, and we did that. Okay, so you should collect them from your friends. Okay, so all of you should be having your own freedom board, okay, from this week onwards. Okay, how you all want to use that board with the boards within your group is up to you. Okay, some of you may everybody wants to open up and everybody wants to use that is fine. Some of you may choose to share one board for the whole semester, all right, and keep the other board or other boards as spare boards. Okay, it's up to you. Okay, if anything goes wrong and all the boards in your group spoil, then you still can use the budget to buy one more additional board. Okay, And of course, as what I mentioned, please go to the makers, okay, at SOC, okay, to print your own 3D casing, okay, so that you can protect your board. Okay, if you remember looking at the video, we have a RAM, okay, and many times your robot is bound to fall off the RAM, okay, while you're still developing and testing your robot. Okay, so you do not want any major damage to your board in that process. Okay, so please do what you need to protect your board. Okay, but of course when you create any 3D casing, uh, take note of the space for the header pins, the power, and so on. Okay, so that you can still access those ports and pins. Okay, so these are the admin matters. If there are still issues with your project group or anything, let me know. In terms of any project components damaged or spoiled along the way, I will do one-to-one exchange. Okay, like I said, except for the Freedom board, anything else that is spoiled, we can do one-to-one exchange. Okay, so you just need to bring your spoiled component or spoiled part to the TA. Okay, then they will take it and give you a new one. So all the other stuff I have spare. Only the Freedom boards I have very limited quantity. Okay, so the project kits, you will start to use some of the material and some of the components along the way. Okay, don't happily take it and stuff it in one corner of your room and then you forget where it is, and then in week 10 you start to dig it out and so on. Okay, so make sure that it is readily accessible by you and your teammates. Okay, if you have friends staying on campus, then probably they will be a better person to keep it, so that if anything is easy to go and grab it and come to the lab. Okay, okay, so let's start with the GPIO peripheral block. Okay, so the GPIO block is definitely the most basic fundamental peripheral subsystem you should learn to control whenever you are starting off on some new embedded board. Okay, so that's how we introduce you to the Arduino Uno. Okay, and it's also how we're going to start over here. Okay, so even in future when you are going to try out some other board, okay, for your project or some other work, the first thing is, okay, the basic functionality of GPIO. How do I do that? Okay, if once you can do that, then you have some level of confidence that the board is fine, that you know how to write the correct libraries or device drivers to control those blocks. Okay, so that is what we're going to be focusing on. In the lecture, I will be continuously switching between the slides, the data sheet, as well as the code. All right, so I will be switching amongst these three because I want you to see the link, all right, between what I am showing in the slides and where this information is coming from and how do we apply it in the code. Okay. Okay, now let's look at these two uh, configure this switch and LED configuration first. Okay, so before we proceed on, okay, let's do a simple poll first. Okay, so looking at this circuitry here, okay, this circuitry that you have, can you answer these two questions? Okay, how do you classify the configuration of this switch, and what logic level at LED 1 out or LED 2 out will turn on the LEDs? Okay, look carefully at the circuit, the way it is configured, okay, and then answer. All right, so this is important because, you know, as computer engineers, as I always say, you're going to be dealing with hardware and software. So you need to make sure that the software you write syncs up with the hardware that you build. Okay, if anyone is not in sync, then the output will not be correct. Okay, so look at the circuit, look at the configuration. It's a very simple design. We have seen this countless time, I think, in EPP1, EPP2. Okay, so I'll just wait for a while. Now it's about 50% voted. Okay, so let me end the poll now. Okay, about 92% have already voted. Okay, and let me share the results. Okay, so for the first question, how do you classify the configuration of the switch? Very close fight between active high and active low. Okay, so about half of you, 45% says active high, 47% of you say active low, 8% say active don't know. Okay, that active don't know will definitely not be a option in your MCQ for your midterm. All right, so you have to probably know what is happening. Okay, so is it active high or active low? So let's look at this switch configuration here. Now, if I look at this switch, what do you see? If I read the voltage at this pin here, you will see that by default, this line is connected to plus VCC. That means it's a high, correct? It's connected to a high. That means if I were to draw the timing waveform, okay, by default, it is a high or a logic 1. All right. But when I close this switch, I will create a short circuit path to ground. Okay, when I close the switch, I will create a short circuit path to ground, and the voltage that I will read at this point will now be the ground voltage, which is 0. So whenever I close the switch, it will go low. Okay, when I release, it will go back high again. Okay, so this is when the switch is closed. Okay, so the active logic of the switch is low, all right, because when I press the switch, then I read a low. So that is why you will consider this particular design to be a active low configuration. Okay, an active low configuration. Okay, so I hope that is clear right now. Okay, so you need to look at what is the logic level you will read when I close the switch. Okay, so in this particular design, the pin voltage, okay, for switch in will be a high by default. When I close the switch, then it goes low. So it's an active low configuration here. Yeah, the small triangle on top is VCC. Okay, so this is ground. Okay, so maybe I should have put that first. So this is your okay, so this is your ground, and this is your VCC. Okay, so if that causes some confusion, then it's fine. But as long as you understand how to relate to the configuration, then I think that is good enough. Okay, for part 2, or question 2, the logic level to turn on the LED, 75% say 1, 25% say 0. So again, you just need to see that the pin here is connected to the anode, okay, of the LED, and you want current to flow from anode to cathode, okay, for the LED to light up. Okay, so in that with that understanding, you know that in order for current to flow, I must have a logic 1 over here. It is a high voltage, then the current will flow and light up the LED. So both the red and blue LEDs are both in the sort of active high configuration, where a 1 will turn on both these LEDs. Okay, so that one majority of you got it right. Okay, so this LED 1 out and LED 2 out are basically the GPIO pins. The same thing as switch in. Switch in, LED 1, LED 2 are all the names given to the GPIO pins that are now connected to these LEDs. All right, so so this is just an example, all right, of the input-output concept. Okay, and we will so to do this in your Arduino Uno and all is of course very easy, very straightforward. Either sketch programming or bare metal programming, you know how to do it. Okay, so now let's move on and understand the Gpio block of your Keil25Z controller. Okay, so this is the Keil25Z microcontroller. Okay, so there are many ports, okay, port A to port E, and each port has a lot of pins, all right, and in if you want to design your own embedded board using this controller, of course, you can decide which port pins you want to bring out or tap out to your connectors and so on. Okay, but because of the fact that we are using the freedom board, that means certain IO may already have been not may not be accessible. Okay, because they've already configured only certain pins to come out to the IO pins. All right, so later on when we look at the lab, okay, we will understand a bit better what is available and what is not. Okay, so even though we have a lot of ports, only a certain number of port pins have been brought out to the connector, so that those pins are the ones that are available for us to use. Okay, now this is the internal of the GPIO block. Okay, as far as what we see externally, we only see this, correct? We only see the pin, all right, the connector socket where we can connect our wire and either use it as input or output, and everything else that you see over here is all internal to the controller. Is internal to the controller. So let's look at how these things work. Now, in terms of registers, there are 6 registers associated with each GPIO port. Okay, and they are mapped to specific addresses over here. Okay, and the order is also fixed. Okay, that means when I say that I'm talking about port A GPIO registers, they will go in this sequence in the hardware. Okay, PDOR, PSOR, PCOR, and so on. Okay, and each register is also 32 bits. Okay, and each set of these registers, okay, these 6 registers control a single port. Okay, that means 6 registers for port A, another 6 registers for port B, and so on. Okay, so that is the control registers. Now these control registers, of course, I've shown you over here. If you were to pick up a microcontroller on your own, okay, and you want to know what are the registers and so on, that is where the data sheet comes in very handy. Correct. So let me bring up the data sheet now. So the data sheet. Okay, so this is the data sheet I asked you to, one of the data sheets that I asked you to download just now. So this is the more detailed, comprehensive data sheet that is focused on the microcontroller itself. The other data sheet, which is this one, is more of the very summarized user manual for the board that you have. Okay, so we will be referencing both, okay, for the lecture and the lab. Now let's scroll down here. So if you look at your left hand side or your bookmarks, okay, if you scroll down all the way, you will be able to see that there is chapter 41, which is general purpose input output. Okay, so while I'm showing you, I also want you to see for yourself, okay, on your own PDF document, so you know where it is and where to find it. Okay, now if you go through this GPIO part over here, you will see that whatever information that I extracted is also directly from here. Okay, so you have the address of the different registers, okay, the information on the width size, and the link to find out more information. Okay, so all this information is over here. All right, so that is the first thing you must understand, that whatever information you want, okay, you can get it from the data sheet. So even if it's not in the slides, you can always go to the data sheet to read out more on each of the peripheral blocks that you're going to be dealing with. Okay, so let's carry on. Okay, so that's the first thing I wanted to show you, that this information is directly available from your data sheet. Now let's look at the different registers. So we saw that there are 6 different registers. The first one is the port data direction register. So this port data direction register is to control input or output. So in this particular controller, it has been designed such that writing a 0 to a bit will make it a input, a 1 will make it a output. Okay, so these are definitely not fixed across different platforms or different controllers. Okay, so some controllers may have it the other way around, where input is a 1, output is a 0. So it's just a matter of looking at the data sheet to understand the information and applying it. Okay, so that is the first register, the data direction register. I think all of us are familiar with that. Next is to write to the output port. Okay, so when I connect an LED, for example, okay, so if I have the port pin here and I want to connect to the LED, okay, so that particular pin is now a output pin. All right, so if I want to write to this pin, I need to write to the data output register, okay, PDOR. Okay, so that is one way of writing to it. Okay, but at the same time, you also have other registers to write or clear or toggle. Okay, so there are 3 additional registers over here where I can say that if I want to set, I can use the PSOR register, so that will write a 1 to that particular bit. If I want to clear, I can use PCOR, so writing a 1 will clear that bit to 0. Or if I want to do a toggling operation, I will actually be able to write to the PTOR register. Okay, so these are just additional registers over that we have to control the output value at the pin. If you don't want to use these registers, you can just stick with the PDOR register and just directly write 1 or 0 depending on what you want. Okay, the other registers are there. You can use them if you want. When I want to read from the input register, okay, you read from the PDIR register. Okay, so a bit of similarity. If you remember your Arduino Uno, you will see that to write to the output, you wrote to the port register. To read, you read from the pin register. Okay, so port B or pin B and so on. So this was for your 8328. Okay, so similarly over here, you also have a separate register for output, separate register for input. Okay, so if I were to connect the pin as an input switch, then I will read the pin port D input register. Okay, in this case. Okay, so this is the pseudo code for the program where we want to control LEDs and switches. I will not go through the pseudo code now. Okay, later on when we're talking about the lab, we will be able to see it a bit more clearly how this works. Okay, right now what I'm going to do is we're going to look at how these registers are actually accessible to us in the software platform that we are using. Okay, so these 6 registers, so these are the 6 registers that we saw just now. Okay, the data register, set register, and so on. And these registers have already been defined or declared for us in a structure, okay, in this header file over here. Okay, so what I'm going to do now is I'm going to move over to our code. Okay, so this week, okay, when you go through the lab manual, okay, so let me jump to the lab manual for a while. So when you go to this for this week's lab, okay, you need to use a freedom board. Okay, you do not need to use any additional hardware because we're going to use the RGB LED on the board itself. Okay, so in the first part here, we are going to be creating our own project. Okay, so this is important because in the previous lab, you just opened up an existing project and downloaded the code just to make sure it was working. And in this lab, we're going to create our own project. This part A is important because in subsequent labs, you're going to be required to repeat this process again, okay, for each new project that you create. All right, so I'm showing you the step-by-step sequence on how to create the project, okay, how to add in the necessary low-level code, boot up code, and so on. Okay, so you just follow through all these steps. And in the first part A, we are just going to be writing a simple code, okay, just to make sure that the code is running and you are able to download it and debug it. All right, and what we will do is we will also introduce you to the idea of putting some breakpoints, okay, and observing the value in your variable. Okay, so in part A, when you start this week's lab, okay, you will just get to see or go through the process of creating your own project. Then in part B is where we're going to be programming the ports. Okay, we're going to be programming the port. So we're going to program the RGB LED on the KL25Z board. Okay, so that is the objective. So we're going to come back to this again later to understand how we're going to do this step by step. Okay, so in your code, all right, when you create the project, you will automatically include this header file. Okay, this is the mkl25z4.h header file. Okay, this header file contains all the necessary declarations, structures, bit mask, and so on that you need for to access all the registers inside the controller. Okay, so everything is already nicely defined for us in this header file. So we just need to make sure we use the correct macros or correct definitions when we write our code. Okay, so we're going to be seeing how it works over here. So for this slide here, where we have this structure. So let's see where this structure is declared inside our header file. Okay, so inside the header file, let me zoom in a bit. Okay, you can see that the registers are declared, okay, in the same sequence as what we saw in our document: data output, set output, clear output, and so on. Okay, and this is already defined as a structure. Okay, this is already defined as a structure inside our code. Okay, now that is basically what you will see over here. Now, if you look at the addressing, okay, so now let's look back at the addressing that we saw just now. For each GPIO type, okay, for each GPIO type, you can see that I need how many registers? I need total of 6 registers. Okay, I need total 6 registers, and each register is actually 4 bytes. Each register is 4 bytes. Okay, so PDOR register is 4 bytes, 4 bytes, 4 bytes. So that's why we use the unsigned integer 32 type to declare the register over here. Okay, that means totally over here, you need the space is 0x00 all the way to 0x17, correct? 14, 15, 16, 17. Okay, so you need a total of 18 hex bytes to store this set of registers for each port. Okay, so for port A, port B, port C, and so on. Now let's look back at our data sheet. Okay, let's look back at our data sheet and look at where we have defined the addresses. Okay, the address is actually here at the side. Okay, so if you see down here, the first address is F000 to 400F F000 up to F014. Okay, so that is where the final register starts for port A. Okay, but for port B, you can see that it starts at F040. Correct, it starts at F040. So if I come back here, all right, that means even though I only use up to the hex 18 bytes over here for port A, my port B only starts at 0x40. Okay, so there is a gap over here. There's a gap of unused space, all right, before the port B starts, and so on. So if you look back at the Datasheet over here, you will see that again when port B ends, okay, when port B ends at 54, it does not immediately start. There is again a gap over here before port C starts. All right. So why do we want to have that gap? Why don't we just save space and put everything one after another? All right. There is nothing else there. All right. So why don't we straight away start the next GPIO block? Why do we leave a gap? Anybody wants to answer? Okay, so there's an answer reserve. Okay, yeah, it's reserved, but why do we want to reserve it? Okay, so alignment is not the main issue here, where everything is still 32 bits. Okay, so everything is still word aligned. Okay, so it is reserved. Okay, that is sort of part of the answer. All right, and why do we want to reserve it? Okay, so that is the key thing. All right, because you will probably see this sort of memory mapping in all the peripheral blocks in other controllers as well. Okay, and the reason why we want to reserve, okay, the reason why we want to reserve is because the manufacturers want to keep some space, okay, for future expansion. Okay, they want to keep some space for future expansion. Of course, they may have other reasons as well, but this is usually one of the reason why they want to keep some space. Why? In most cases, your controllers will evolve over time. Okay, so right now they have this KL25Z. All right, then later on they may have a slightly upgraded version. All right, and when they create a slightly upgraded version, they do not want to reinvent everything. All right, they want to leverage on whatever they have already done. So if they have ideas to enhance the GPIO block by adding more functionality, then they can make use of this space over here to add in additional registers. Okay, so in most cases, you will see reserved registers or reserved space in between some of these peripheral blocks that you are dealing with, and those are generally used for future expansion by the manufacturer. Okay, so in future when you upgrade to a slightly better version of this same microcontroller, you may see that hey, instead of 6 registers, suddenly I got 8 registers, or I got 10 registers, and so on. Okay, because now you have more functionality. Okay, so that is one of the reasons. Okay, so in terms of programming, okay, you do not need to worry about these actual addresses, okay, where it is defined and so on. What it is already done for us is the base address has been defined in the header file, and there is also a definition, all right, where we have created a pointer to the structure type, okay, with the base address of each of the ports. All right, so all you need to do is use the notation of a structure pointer. Okay, structure pointer. So in this case, PTA is a pointer that is pointing to the elements of the structure. All right, and the base of this structure is already been defined for us over here. Okay, so when I use this notation, okay, what is happening is PTA is pointing to the address 0x400FF000. Okay, and in that address, the first 4 bytes, okay, and when I say PDOR is also defined to be the first 4 bytes over here. Okay, so by using the pointer to the structure, I can access each of the registers directly, okay, using this format over here. Okay, so the header file, okay, this header file already has given us all these definitions and pointers and structures very nicely for us. So we just need to use them in our code. Okay, so let me show you in the code itself. So this is the structure just now that we talked about. Okay, and this is the definition of all the bases. Okay. So this is the where we have declared the base address for each of the GPIO block. All right, we define the base pointer, and then we can use this base pointer GPIO A or GPIO B and so on to write our code. Okay, at the same time we can also use this to we also will be looking at the mask in a while. Okay, this is the mask, and these are the definition for the structures. Okay, so everything is nicely defined for us to use. Okay, GPIO type base A. Okay, so what is that? So this is basically telling us that this PTA base is actually defined to be this address, correct? And now I am saying that I am defining PTA to reference this base address as a pointer to a structure. Okay, because GPIO type is actually defined as a structure, right? In your earlier slide, GPIO type is defined as a structure. Okay, we already defined it as a structure. But now I'm using this notation to be a pointer to a structure. So when it's a pointer to a structure, when I want to access the individual elements of the structure, I use the arrow, okay, to point to each of the elements in the structure. Okay, so that is what this definition is doing for us. Okay. Okay, so that is the good part of using this platform, that we're using the Keil IDE environment. All right, all of these definitions are already there for us, so we just tap onto them. Now, in terms of the coding style, all right, we need to, of course, make sure that you implement proper coding techniques. All right, so what are proper coding techniques? So you need to use proper hex defines for your constants, and use proper masking techniques to extract out the bits that you are interested in. All right, now take this example here. If I want to set bits 13 and 19, okay, if I use a binary bit mask like this or hex bit mask like this and do a OR operation, yes, it can work. Okay, but it's obviously not the right choice, okay, because you can make mistakes either in the binary or the hex representation. The other way is, of course, you can do something like this, where one shift left 19 or with one shift left 13. Okay, that means a bit one, you shift left by a certain number of times. All right, then you OR with another one shifted left by another number of times, and you OR them together, so you get this particular end, which is going to be the same as what you have here. Then a slightly better version would be, instead of putting 19 and 13, you define them. All right, so this is my green LED, this is my yellow LED, and so on, and then you shift based on that. All right, the other better option is, now you declare a universal mask function, where this mask macro will take in X and you shift one left based on the X value that you pass in. All right, so when I say mask green LED pause or with mask LED pause, I will take these two values, sorry, green LED pause or with mask yellow LED pause. So this, what will it do? This is equivalent to actually doing this. All right, so this and this are the same. They're the same. Only difference is, instead of explicitly writing one shift left by so many bits, I use the generic mask function. Okay, so this mask function is actually very useful for us to do bit masking. We have done bit masking before, right, in EBP2. So now we're just using a slightly different version by using the mask macro. Okay. Okay, so ULs, you will see this quite often in all your code. UL is just to specify it is unsigned long. All right, it is just an additional sort of term you can put together with your number, but it makes no difference with or without UL. Okay, so you don't need to worry about the UL. Okay, so even if we just write it as 1 shift left 13 is still fine. Okay, so using mask, we have let's can have a quick recap. This will basically override. So when I use the equal sign, I will take whatever is the result of this masking function and override whatever that was in N, correct? But as we have seen before, in many cases, you may not want to override, correct? Given a 32-bit register, okay, you may only be interested in maybe changing the value in bit 7, bit position 7. All right, you do not want to touch the rest of the bit. So in those kind of cases, you have to do the proper masking technique, which is to either or, which if you want to set, or you do the AND if you want to clear. Okay, so you've seen this before. So it's about making sure you only change the bits in those positions that you want to change, while the others are unchanged. All right, so this is important, okay, because sometimes instead of using the or and, we directly override, and what happens is a previous functionality is suddenly not working anymore. All right, after you add this new functionality, because you, instead of doing the masking, you overrode the value. All right, so that is something you need to be careful about. Okay, if you want to complement, all right, you can always do the complement using the tilde sign over here. Okay, so let's look at the C code over here and try to understand what is happening. Okay, so let me come to this. Yeah. Okay, so this is the same C code that we saw there. Okay, so what is happening here? So the first thing that is happening here is we have defined a mask, okay, which is 1 shift left by the value that you pass in X. Now for the first line over here, what is happening? Okay, so let me go through in detail first. Okay, only in this lecture, I'll be going through everything in very detail so that you understand what is really happening. In subsequent peripherals that we will be covering, I will not go through in depth, because I expect that you already know where to get this information from the data sheet and so on. Okay, so some aspects we will go through in more detail for today. Okay, so for this first line, I'm saying that port A PDDR or equals this particular line. So mask LED 1 pos, mask LED 2 pos. So let's just make sure that everybody is clear what is happening. Okay, so when I do this LED 1 pos, what is happening? That means effectively I'm calling this mask macro, passing in LED 1 pos, which is 1. So 1 shift left by 1, okay, will give me mask. Okay, so 1 is originally over here, then I shift left by 1, it will come over here. Okay, so this 1 will no longer be here. Okay, so this is bit 0, this is bit 1. Okay, so that is what the first part of this instruction will do. Then the second instruction, I shift left by 2, LED pos is 2, so I will create another one more over here. Okay, so that is for this. Okay, and I'm doing an OR operation with port A PDDR. Okay, so what is PDDR? Is port data direction register. Okay, so port data direction register, and writing a 1 to the PDDR. So writing a 1 to port A PDDR means port A, bit 1 and bit 2 will be output. Okay, so this will make sure that port A, bit 1 and bit 2 are output. So they're configured as output. So that is the first line. In the second line over here, I am doing a AND operation with the complement of mask switch 1 position. Okay, so mask switch 1 position. So switch 1 position is 5. So basically for bit position 5, so this mask switch 1 position will put a value of 1 into the position of bit 5, correct? And then I am doing a complement of it. Okay, so originally this mask switch 1 position will create 1 and everything else will be 0. Okay, after I do the complement, what will happen? It will become inverted, correct? So the 1 here will become a 0. Okay, and everything else here will become a 1. Alright, so that is the mask, and then you do the complement. And I'm doing a AND with the PDDR. Okay, so I'm doing the AND with the PDDR. So this is where the correct masking technique matters, because in the first instruction you have already configured bit 1 and bit 2. So this is bit 1 and bit 2. You configured them to be output. So you do not want to mess it up. Right? You do not want to mess it up. So that is why we are doing the proper technique of doing an AND with a 1. Because when you do an AND with a 1, nothing changes. Correct? But when I do an AND with a 0, this one will become 0. Okay, so as far as bit position 2 and bit position 1 is concerned, they are still being retained. Okay, the value in them is still retained as 1. Okay, from the earlier configuration. Okay, so these proper techniques are important, okay, to make sure that when you are trying to manipulate multiple bits in the same register, you do not mess it up. Okay, so that is your PDDR register. And in this line, you are writing to the PDOR register. Okay, so mask LED2 pos basically means that in LED2 bit 2, I am setting the PDOR bit to 1. Okay, so in my port A, okay, in port A, I have bit 2 and bit 1, and both of them connected to LEDs. All right, by setting this to a 1, I'm writing to this or making this LED light up. So this LED will light up. So that is what I'm doing, turning LED, I think it's LED 2, correct, and turning off LED 1. Okay, I'm turning on LED 2 and turning off LED 1. Okay, then in this loop, basically what is happening is I'm reading from the switch. Okay, so in port A, okay, in port A, pin 5, so in pin 5 you're connected the switch, okay, and you are trying to read the switch. So since I'm reading the switch value, I need is an input, so I need to read from the PDIR register, port data input register, and I'm doing a mask with the switch 1 position. Okay, so why do I need to do the mask here? Because when I read the register, I'm reading the full 32 bits. Correct, I'm reading the full 32 bits, but I'm only interested in bit 5, correct, because only bit 5 is connected to my switch. So I do the AND with the mask. And when I do an AND with a mask, so in this case, if it is a logic 1, if it is a logic 1, the switch is not pressed. Okay, the switch is not pressed, because you have to remember that our switch that we connected was actually active low. Okay, from our first second slide that we saw just now, the switch is actually configured to be active low. All right, so in this case, if it is if I read as a 1, the switch is not pressed, then I activate LED 2. All right, and in this, okay, so here when I do this, okay, what am I doing? I am switching on LED 2. All right, because PDOR register, I am writing to LED 2 position. If not, if the switch is pressed, I switch on LED 1. Okay. Now, there is no explicit right or switching off of the other LED, correct? When I switch on LED 2, I never explicitly switch off LED 1. Similarly over here, when I switch on LED 1, I never explicitly switch off LED 2. But it still works that way because I am doing a direct write. I'm not doing bit masking here. Okay, if I were to do bit masking, all right, then it may be a case where I need to explicitly switch on and switch off each LED. When I directly write, I know that only that particular LED or that particular bit is set to a 1. Okay, the rest will automatically become 0. Okay, because when I do the mask function, only that 1 is shifted, everything else is 0. Okay, so the way you write your code, okay, whether you use bit masking, whether you use direct write, okay, all these are important. Okay, and this can cause a lot of confusion in your lab. Okay, because if you write it in a particular way without realizing, then when you are trying to test it, you may not see the correct output, but actually it is correct. It's just that your driver was written to either use bit masking or not, and then you see some other funny behavior. Okay, so later I will show you more on that when we are discussing the lab. Okay, so everything is directly interpreted as 32-bit. All right, because we are dealing with a 32-bit register. Okay, so when you are doing masking, you're shifting, the data is automatically interpreted as 32-bit. Okay, so that is how you must think when you are writing your code. Okay, so okay, so right now is 11 o'clock. We will go for a short 10 minutes break and we come back. There is a request to explain the if statement again. I will explain again. Those of you who want to go for a break, you can go for a break and come back in 10 minutes. I will just explain the if condition again for those who are not clear. Okay, so it's a break time. Okay, please go and come. I'm just going to explain the if section again. Okay, so for this if section, all right, basically you are reading. So this is the part where you read from the switch. Okay, because the port A is configured to I mean, when you read from the PDI register, port data input register, you are reading the bits, okay, that are going to be configured for input, and you are now doing a mask with the switch 1 position, okay, because you may have other pins also configured to be input, so you only want to focus on your switch 1 in this example, so you only want bit 5. So when I do the AND, I'm going to read the value at bit 5. Okay, so when I read the value at bit 5, okay, if you look back at our configuration of the switch, okay, the switch is actually, I have it over here. Okay, so if you remember our configuration of the switch, okay, by default, it is a high, it is a 1. Okay, but the moment I close the switch, okay, I create a short circuit path to ground. So whenever I close the switch, it goes low. Okay, and then after that, it goes high again. All right, so the pressing of the switch, okay, is here, 0. When I don't press, it is high. Okay, so with that understanding, when I read, when this if condition is true, if this if condition is true, okay, means it is actually reading a logic 1. Okay, so if it's reading a logic 1, means that the switch is still not pressed. Okay, that means I'm still pulling it up. The switch is not pressed. Okay, so if the switch is not pressed, then I light up LED 2. Okay, so the moment the switch is pressed, then the logic will become 0. So that is when the else condition will be satisfied. Okay, so this is again just an example of a particular switch and particular LED only. All right. In other situation, if my switch was in the active high configuration, then it would be the other way around. Correct. That means I want to turn on the LED when the switch is pressed and turn on another LED when the switch is not pressed. Okay, so it's just a matter of relating the software to the hardware configuration that you have. That's all. Okay, so when you read from the PDIR register, you will read in the entire 32 bits. Okay, but it is the masking that will help you to make sure that you are only looking at that particular bit file. All right, then you can make the decision based on that bit file alone. So that is why the masking is important, to make sure you only look at the particular bit position. Okay, so let me go for a break as well. I will see you all back here at 11:10. Okay, so now it's 11:03. Okay, so I'll see you back here at 11:10, and then we'll carry on. So I will, in all likelihood, go all the way to maybe 11:45, 11:50, and so on. If you have another class that you need to go for, all right, and you want to log off earlier, is fine. You can always check the video. All right. So we're going to finish up these slides, and I'm also going to do a demo on the lab as well. Okay, so you know how to proceed with this week's lab. Okay, so let's carry on. Okay, so this is where we stopped just now. Okay, on the code analysis. Now, this is another important part which is can be easily forgotten and can also cause some issues later on, which is your clock gating. All right. Unlike your Arduino Uno and so on, where by default everything is powered up and ready to use, in the KL25Z board, the most of the peripheral blocks are actually switched off, okay, by default. Okay, that is to make sure that we can save power. All right, so when you are writing, okay, or before you start to configure any part of the registers associated with any particular peripheral block, you need to make sure that that particular uh, peripheral block has already power enabled to it. All right, so there are a few different registers uh, for the uh, different peripheral blocks that we have. For the GPIO ports, all right, there is one particular register called the SIM SCGC5. Okay, so let me show you that in the data sheet. Okay, so in the data sheet, if you look under chapter 12, okay, system integration module, okay, there are a few different registers here. Okay, and one of them is the system clock gating control register 5. Okay, so there's 4, 5, 6, 7, and so on. Different registers of different peripheral blocks. If you look at SCGC 5, you can see that that is used for your port power control. Okay, that means if I want to enable power to any particular port, I need to come to this register SCGC 5, and I need to write a 1. Okay, so you can see if I want to use port A, for example, by default it is disabled. If I want to enable it, I must write a 1 to it. Okay, so I need to come to this register and write a 1 to this particular bit over here. Okay, then I can start to use the peripheral registers and do the necessary configuration. Okay, how do I do that in the code? Okay, so this is basically what you need to do before you can actually start to use the block. And you can directly use the definitions given to us by the header file. Okay, so inside the header file, okay, you directly can use the again pointer to structure pointer notation. Okay, so this is a very common programming style you'll be using in this module, where you have a base pointer pointing to the structure, and within the structure, all the register files have been defined. And for each of the register files, you can use one of the existing hex definitions or macros to configure that particular bit to a value. Okay, so let me show you this. So this is actually from the code. What you will see is you will see macros like this very often. So for SIM SEGC port AX, okay, so what is happening here? So if I were to write a 1, if I were to call this function, okay, so instead of SEGC5 port A mask, if I were to write it as SIM, okay, SEGC5 port A, and I put a 1, then what happens? All right, so the 1 is the X, correct? So the X here is a 1, and I shift left by this amount, which is port A shift. And how much is port A shift? Port A shift is 9. Okay, why 9? Because it is actually referring to bit 9. So if I look at the entire SCGC5 register, the full 32-bit register, bit 9 is the one that is controlling the clock gating for port A. Okay, it's controlling the clock gating for port A. Okay, so I'm going to shift left, the 1 I'm going to shift left, so I'm going to get a 1 here, and then I do an AND with this mask. Now what is this mask? This mask is actually all zeros, and there is also a 1 here. Okay, and bit 9, because this 0x200 actually translates to this. Okay, this is if you can't see it clearly, this 00 is basically from bit 0 all the way to bit 7, and this 2 here is 10, correct? That means this is bit 8 and this is bit 9. Okay, so that is 10 here. Okay, so the mask is to make sure that I only have that single bit. All right, and I'm going to do a OR operation, or I can do a direct write. So in this case over here, I do a OR operation. Okay, again, this is important because your project and so on, you will probably be using multiple ports, okay, which need to be powered up at the same time. Okay, so you do not want to directly do a write and then switch off the other ports. Okay, so the OR operation ensures that you are going to do a or write a 1 to this particular bit without affecting the other bits. Okay, so in this example here, is actually basically just a shortcut method. Okay, so instead of using the macro, what they have shown here is you directly use the mask. Okay, and why does this work? Because in our case, we want bit 9 to be set to a 1. Correct? We want bit 9 to be set to a 1. Okay, and that is actually what this mask is already doing for us. Correct? Because if you look at this mask definition is already setting bit 9 to 1. Okay, so instead of using my macro, I can just use the mask and it still works. Okay, so you can use that as an option. Okay, and of course this only works in this particular kind of cases. Why? Because I'm changing only a single bit and I want that bit to be a 1. Okay, so it's easy to just use the mask to directly do a OR. Okay, but in other cases it might be better and safer to just use the macro that is given to us. Okay, so these are also given in the code itself, the code base. Okay, so if you come here, okay, so you can see down here all the SIM, SCGC registers are defined here. Okay, so the macros, the definition, everything is defined in the header file itself. Any case, this header file, okay, is the file that you should always reference back if you want to look at any definitions, macros, and so on. Okay, so everything is inside this header file. When you start lab 2 and you create the project, this header file will be there. Have a look at this header file so you know all the definitions that you have, all right, and then you will slowly be using them along the way. Okay, so the last part is multiplexing. Okay, this is also another important thing that can easily be overlooked. All right, as we have seen before with the Arduino, Uno, and other controllers, every pin on a microcontroller is heavily multiplexed with a lot of functions. All right, that is because you have limited number of pin count. All right, so you need to make sure that you connect or you configure the correct pin. So in this case, GPIO is only one of the pins. Okay, and that particular pin might be used for I2C bus, PWM, uh, timer, and so on. Okay, so it can be have a lot of different functionalities. So this has to be configured in another register called pin control register. So this pin control register is shown here, where, okay, so instead of showing you here, let me go back to our data sheet. Okay, so as you can see, I always try to go back to the data sheet, okay, because that is always the first point of uh, information source for you. All right, because when you are able to get the information from the data sheet, you need to worry about anything else. All right, because everything is there. Okay, so for pin control register, let me just do it. Okay, it's here. Okay, so this pin control register, as you can see here, is giving you the ability to configure the functionality for each pin individually. Okay, so it is not a port level configuration, it is each pin individually. All right, so given any port, I can take port A, I have 32 bits, I can configure each pin individually for any particular function that I want. All right, and that is actually through these 3 bits over here, bit 8, 9, and 10, which is the marks option. So, so if you look at this marks option, you can see that the 000 is disabled. That means you use it as analog. Alternative 1 is used for GPIO functionality, and 2 to 7 is chip specific. Okay, so when you say chip specific, that means it depends on that particular version of the microcontroller you are using. All right, so let's see where you can get this information. So if you go back to your chapters here, okay, there is a chapter here, chapter 10 on signal multiplexing. So you click on this signal multiplexing, you will see that you will come to this particular table here, KL25, signal multiplexing and pin assignments. So this is where you have the alternate functionalities. All right, that means, for example, I want to use port E pin 0, for example. So port E pin 0, as we have seen, the alternate 1 function is always the GPIO function. All right, but if I want to use it as a UART pin, okay, for my serial transfer of data, I can use it as alternate 3. If I want to use for I2C data, I can use it as alternate 6. All right, so you need to configure the correct multiplexing option, okay, as you go along and you start to use other peripheral blocks. Okay, for GPIO is easy because it's always alternate 1. Okay, but for other peripheral blocks, you need to check this table to see which function or which alternate function it maps to. Okay, so this is the multiplexing that you need to be aware of, okay, when you are going to use your blocks. Okay, so for our case, what we need to do is we need to make sure that the bits here, which is 10, 9, and 8, okay, marks is configured to 001. That ensures that it is going to use the GPIO functionality. Okay. Okay, so this Pcr register is defining the configuration for the pin, okay, or for each pin across all the ports. Okay, each pin across all the ports. So you have PCR register for all the pins. Okay, so let me show you here again. Okay, so over here you can see that I have pin control register for port A, bit 0, bit 1, bit 2, all the way, okay, until bit 31. Okay, and then again port B, pin control register 0, 1, 2, all the way. That means you have, if my port has 32 bits, I have 32 registers of PCR functionality to control each bit separately. Okay, so you need to make sure you configure the correct register depending on which bit you are going to use. Okay, and all of this is also defined for us inside our header file. All right, so inside our header file, you can also see the structure, okay, where you have the PCR register defined with the port type definition. Okay, so inside um, uh, your Keil environment, okay, we have already seen the port A base, okay, and the definition, okay, that is for the port that we're going to use. In terms of the PCR, all right, what we can do is we can actually use the Pcr multiplexing macro over here. Okay, so what does this macro do for us? Okay, so in terms of port type, okay, this is the port A base and this is the definition of port A. This points to the port type. Okay, so the port type is, okay, so let me show you here again. Okay, so for each of these registers, the pin control register, okay, you need to configure the functionality. Okay, so pin control register here. So you can see the definition here that I need to map to the particular port type. So this port type here basically gives me the mapping to the 32 bits for each of the bits for each port. All right. And then what I need to do is I need to make sure I point to the correct bit and then I do the correct configuration. Okay. So in terms of the configuration, okay, we use this macro over here. Okay. So this macro here, what it does, it takes an X value. So in this case, for example, I want it to be configured as GPIO. So I put a value of 1, all right, because the max value has to be a 1. And this 1 is shifted left by 8. Okay, why 8? Because in my full 32 bits, I want the 8, 9, and 10, correct? These 3 bits are the one that reference my multiplexing. All right, and then I do an AND with the PCR max mask. The mask is always created such that the bits that you want will be a 1 and the rest will be a 0. Okay, so this actually translates to this. Okay, now in this example, you can see that I cannot do the shortcut method earlier on because in this case, I do not want to set all 3 bits to 1. Okay, if I do a OR with PCR max mask, if I do a OR with this, what happens? That means I will automatically select the alternate 7 function, correct? Because this will be 1. Okay, in this case, I'm only wanting to put a value of 1. So what I'm going to do is 1 shift left by 8. So this will give me a value of 0, 0, 1 in this bit position here, 0, 0, 1. Okay, and then I do an AND with my mask. So when I do an AND with my mask, okay, so this all this rest will be 0. So when this and this, I do an AND operation, what will happen? What is left is going to be 0, 0, 1. correct? Because 001 end with 111, I will get 001. And then I will be able to do the correct OR operation to put it inside the register that I am writing to. Okay, so let's see how to do it. So in this case, okay, if I want to write, okay, so let me just show you this one example. The rest is the same. Okay, so in this example, what you're doing is this first line here is to enable clock to port A. All right, as we saw earlier, SCGC5 is the register that is controlling the clock gating for all the different uh, ports. I mean, for the GPIO ports. And by writing a 1, you are going to enable that particular port. So this one is to enable the clocking. Okay, once I enable the clocking, I need to configure the multiplexing. Okay, so for the multiplexing, uh, what am I doing? I'm doing 2 steps here. So for port A, so the way in which you will code is you will use the point A as the pointer to the as a structure pointer, and you're going to point to the PCR register. The PCR register itself for each port is 32 bits. Okay, the PCR register itself is 32 bits. Okay, why 32 bits? Because there is an individual register for each bit. Okay, so in this case, I'm only going to focus on LED 1. Okay, so I'm passing the index for LED 1. Okay, and in this first line, what am I doing? I'm doing an AND with the complement of the PCR mask. What is the PCR mask? It is this. Okay, so the PCR mask, okay, the mask is such that 8, 9, and 10 is 111. The rest is all zeros. Okay, so that is the mask. If I take the complement of the mask, what happens? Okay, I'm going to put all zeros and the rest is all ones. And then I do an AND operation with the PCR register. All right, so what will happen? That means for this particular register, which is PCR LED 1, the 3 bits here, 8, 9, and 10 will become 0. So I am first doing a reset to the default configuration with all 0, and then I'm doing a OR, okay, with the port PCR max 1. Okay, so in the next line over here, what is happening? Okay, so for this next line, what is happening? I'm doing an OR with the port PCR max 1. So this is actually the use of the macro over here. So when I call port PCR max 1, what I explained is happening. That means I'm putting a 1 into the X. I'm shifting left by 8. So the 1 comes here, 8, 9, and 10. Then I do the AND with the max, which is to make sure that I only keep bits 8, 9, and 10. All right. And so the final value will be the entire 32 bit, but 8, 9, and 10 is reflecting the value that I passed into X. Okay, so this one macro port PCR max X does all this for me. Okay, so when I call this port PCR max 1, what is happening is it automatically does all this masking for me in the background and make sure that bit 1 or this value 1 is in the bit position 8, 9, and 10. Okay, that is what the macro is doing for me. And when I do the OR operation here, okay, when I do the OR operation, I am making sure that only the bits 8, 9, and 10 of the port of the PCR LED 1, okay, only these 3 bits have a value of 0, 0, 1, and the rest will be unchanged. Okay, so it will be unchanged. Okay, because I'm doing the OR operation here. Okay, so it is a 2-step process. The first step is clearing the 3 bits, and the second step is updating the 3 bits with the correct multiplex setting that you want. Okay, so you just need to do this for each of the GPIO pins. Okay, so once you do that, you are able to configure the pin as input or output. Okay, so that these next few slides, okay, are not so critical. You can just go through. But what I want to do now is I want to switch over to the lab, okay, to make you understand what is happening. Okay, so we are going to be using all this information, okay, for the lab. So in the lab manual, okay, we are going to be using the board. So let's look at the board in a bit more detail. All right, so what we have here is the Freedom board. Okay, we will be going through this document again quite frequently, okay, for different parts of the module. So let me scroll down here to the portion on the RGB LED. Okay, so if you have your document, you can open it up as well. Okay, in page 11, you have the RGB LED. Okay, so if you look at the RGB LED over here, let me bring it up here as well. Okay, now can you all tell me, looking at this RGB LED sort of schematic diagram, can you tell me whether the RGB LEDs are active high or active low? Okay, so most of you okay, mostly correct, is active low. Okay, why is it active low? Okay, basically you can see that pin 2 is connected to 3.3 volts, and that pin 2 is connected to all the anodes of the LEDs. All right, so in order for me to switch on any LED, the cathode must be driven low. Okay, the cathode must be driven low, then I will be able to uh, drive or light up the LED. Alright, so the active logic always depends on what is the voltage I need to apply to activate this particular device. So in this case, all three RGB LEDs here uh, need I need to apply a low, then only current will flow. So we say it is an active low configuration. Okay, all the anodes are connected together and brought up to 3.3 volts. Okay, so that is again it's important to be able to look back at some of these schematics, okay, and understand the hardware configuration of your board. Okay, now let's look at the code and the hardware here. So we are given that the RGB LED is connected to this port. So you have port B and port D. Okay, port B and port D. So I need to make sure that all these three pins, port B18, port B19, and port D1, are all configured as GPIO. I have to enable the clock. I need to do the multiplexing. Then I can go ahead to do the actual code. All right, so remember that there are few things you need to do before the actual logic of your code can come in. All right, you need to enable the clock, you need to do multiplexing, you need to set the direction and so on. Then the actual logic comes in. All right, so let me give you an idea of how you can do this. All right, so firstly, of course, you want to be able to define these LEDs in your code. Okay, so you do not need to follow what I have shown you. You can create your own device drivers to control your LEDs. Okay, I'm just showing you one example only. Okay, then the first step is, of course, you want to enable the clock. So in the init GPIO function, I have this line here to enable clock to both port B and port D. So this will ensure that both port B and port D have power. And then subsequently, the next step is multiplexing. So the multiplexing, we have seen that what I need to do, first step, I clear the current multiplexing bits in the register, Pcr register, and then I set the correct multiplexing value. Okay, so that is what I'm doing here. Okay, for the red LED, green, and then the blue. Okay, so now I've done the first two steps: enable the clock, configure the multiplexing, And then the last step is configure the their direction register. Okay, so in this case, since I have two separate ports, port B and port D, I do it separately. So one for port B, one for port D. Okay, so in this case, I use the mask macro that we saw in just now in our slides. So this make sure that the bit one configures those bits to be output. Okay, so with this, all your configuration, everything is done. Then you can just write your code. Okay, so in the code that you're going to write, you can do whatever way you like. Okay, for now, when you want to create a delay, I've actually provided a delay routine inside the Luminous as well. Okay, so that just gives you the ability to create uh, some random delay in the code, or fixed delay in the code that so that you can see the LED blinking. Okay, so you can use that code, or you want to write your own delay routine is also up to you. Okay, but this is basically what I've given to you in the Luminous. Okay, again, the controlling of the LED behavior is up to you. Okay, um, what registers you want to use. In this example, okay, when I want to switch, I did not specifically have separate on, off, and toggle or things like that. All I did is I just use a single function, and depending on which color I pass in, I use the PCOR register. Okay, the PCOR register is basically port clear the output register. Okay, so when I clear means I'm going to write a zero, or logic 0 is going to be on the pin. Right. So by writing a 1 to the PCOR bit position, 0 or logic or voltage 0 appears at the output pin, and that will allow the LED to light up. If you don't want to use PCOR, you can just directly use the PDOR, which is directly writing a 1 or a 0, okay, to the bit that you want. So it's up to you how you want to control. If you want to have multiple functions, okay, one to on, one to off, one to toggle, and so on, is also fine. Okay, it is important that you have a good understanding of what you are doing. Okay, exactly how your library functions are working. All right, because you are going to be using your library functions throughout this entire module. Okay, so you want to write your own library code that you are comfortable with, that you know, okay, if I call this function, I will on the red LED. If I call this function, I can off the LED. All right, or if I want all three LEDs to be on or anything like that, this is how I do it. So you must know how you are going to use your own library function. Okay, now what I'm going to do is I'm just going to compile this code, and I'm going to run, and I'm going to show you what happens. And the one more thing that I'm just going to show you is how to check back on the actual hardware of your system. All right, so give me a minute here. Okay, so right now, what you're seeing is this code. Let me download it again, okay, and you can see. Okay, so in this code that I've written, it is just basically to just go through the RGB LED in quite a fast rate. Okay, so this delay function can be used. You can increase the number or decrease it if you want a slower or faster blinking rate. All right, and the whole idea of the lab is, of course, just to make sure that you get familiarized with the GPIO module. You can write your device drivers correctly, and you see this effect. All right, the next step is, of course, this header pins, like I said, they are not necessary for now. But if you are going to go ahead and solder the pins, okay, you can also try one more thing, which is to actually monitor these pins or the output on the oscilloscope. Okay, so that is what I'm going to show you now. Okay, coming back to our data sheet here, you can see that we have the three LEDs mapped to port B, pin 18, pin 19, and port B1. Now, the next uh, thing that you need to be again referencing very often is this particular mapping. This is very important because this picture here, okay, this diagram here shows you the actual pins that are accessible to you through the connector pins. Okay, and this is important because this is basically what you have to deal with when you're building up your project. Okay, what is not available on these connector pins, you won't be able to tap them out. All right, so you have to rely on these pins. Okay, they are more than enough. All right, but these are the ones that are available to you. Now, can you tell me out of the 3 LED pins, which one is available for us? Okay, can you look back and look at this and tell me the 3 LEDs, which pin can I actually tap out over here?
Sorry, Prof, can you repeat the question?
Okay, so my question is, I have 3 pins for the RGB LED, correct? 2 connected to port B, 1 connected to port D. So these 3 pins, which of these 3 pins is actually available on these connectors? Okay, yes. Okay, so those of you who found it, you can see that only port D pin 1, okay, port D pin 1, this here is available. The rest of them, they are already internally connected and they are not available. Okay, of course you can still try to tap it out, but there's a high chance you will damage your board if you try to do something funny like that. All right, so don't try to tap onto other test points on the board. Okay, just stick with the connectors that are available to us. Okay, so now what I'm just going to show you is how you can use your connectors once you have soldered them to tap out the signals and see for yourself. All right, so now coming back over here, let's relate this to our picture here. Okay, so let me do a close up here. Okay, so you can see that when you look at the board, okay, the numbering, when you look at it, you should look at it in this way, where on the top here is the touch screen, which we're not using. Okay, and your 2 USB connectors are at the bottom. All right, so please make sure your orientation is correct when you're trying to relate the connector and pin out. Okay, so for port D pin 1, okay, it is basically the bottom left corner, and the pin is, okay, so I need 2 pins, correct? I need the ground pin and I need the port D pin 1. So 1, 2, 3, 4. Pin 4 from the bottom left is ground. Pin 5 is port D1. Okay, that means over here, what I need to do is I need to count, all right, and see that it goes up to pin 4 for ground and pin 5 for port D1. Okay, so that is what I'm going to do now. I'm going to connect up my scope. Okay. Okay, so that is my ground pin 4. Okay, I mean the 4th pin from the bottom left, and then I'm going to put in my next pin is one higher, and that will be my port D1. And then now you can see the waveform appearing on my scope over here. Okay, so that is basically how you can actually be tapping out your signal to see what is happening. Okay, and if I zoom in, let me check the cursor here. Okay, so if I move the cursor for the measurement, okay, okay, you can roughly see that the VPP, okay, so let me zoom in here. Okay, this VPP is around 3.3 volts. Okay, so your signal that you tap out, okay, from your GPIO pins is 3.3 volts. Okay, so that is also indicative that your controller is also running on 3.3 volts. Okay, so this part, the power part, the voltage regulation, you will look at it at a later time. All right, but this is basically what you can do for this week's lab. Okay, so for this week's lab, okay, you do not need to come to the lab, you don't need to solder the pins yet, but if you have soldered them, all right, and you want to see these signals for yourself, you can actually do that. All right, and of course, like I said, try to be very careful with your soldering. Okay, and once your soldering everything is done, okay, try to make sure that you put some protective casing over it so that you do not accidentally touch any of your the components on the board. Okay, so that is the objective for this week's lab. All right. Uh, as long as you are able to apply the GPIO concepts, create your own device drivers and everything, all right, then I think you're good to go. All right. Uh, Please do work on the device drivers libraries yourself, like I said, because you will be using them extensively. So you need to be really clear on how it is working. Okay, many times I've seen students who uh, develop code later on, and then they think that it's not working because the LED is off, whereas it should be blinking or something. But then it is not the case where the code was not working, but your driver was written in a way that the moment you try to switch on one LED, the other LED went off or something like that. Okay, and this is especially important because in some of the labs, I will have certain requirements where I only want red and green to be on, blue to be off, or something like that. Okay, but if your device driver is written such that only one can be on at a time, okay, or when you switch on one, automatically you switch off the other, then this kind of functionalities you will have difficulty implementing. All right, so try to create proper library functions to control LEDs individually and also to control them together. That means if I just want a red and green, how do I do it? If I just want blue and green, how do I do it? Okay, so your drivers must be able to handle this kind of different LED combinations. Okay, so that's all I have for today's lecture. All right, any questions you can ask me. Okay, so there's a question on how do we know D1 is accessible. Basically, you just need to look back at this pinout over here. So this connector pinout, you have all the port and the pin numbers, correct? So you can see that my LED is connected to port B18, port B19, and port D1. But when I look back at the connectors here, I do not see port B18, I do not see port B19, I only see port D1 over here. All right, so you need to be, you are sort of limited to what you have brought out to your connectors, and that is what you can use for your project as well. Okay, so of course this is, you will use it more in subsequent weeks when we start to look at interrupts, PWMs, serial interface, and so on. Okay, so okay, port B18 and port B19, again, they are not hidden in a sense that basically you have limited space, correct? So the limited space means they've only decided to bring out these pins to the connectors, so you can't use port B18 and 19 for anything else. All right, so whatever is not available here on these connectors, you can't use them for anything or for any particular way of interfacing to an external peripheral. Okay, you are only limited to what you see in your connectors. All right, basically I would say it's more of a space constraint, and in some cases in terms of multiplexing, they may have already decided that certain parts of the microcontroller will be used for specific uh, multiplexing options, because you have already connected the maybe touch sensor over there, you already have a different type of interface and so on. Okay, so some of the multiplexing options may not be available or may have already been used up by the way the board is designed. Okay, so that is again a standard limitation, correct? Whenever you use any readily available board, you have some limitations and you work around them. Unless you build your own embedded board with the microcontroller on your own, then you are free to use anything you like. Okay, so that's all I have. Thank you very much. Yeah, so I will upload whatever slides and material that I have. Okay, and at the same time, the video will also be uploaded. Okay, for you all to review. Okay, and recap when you are preparing for the lab. Okay, so any other questions you can ask me. If not, thank you very much. I finished before 12. That is an accomplishment for me. Okay, so thank you, and I will. So on Friday, those of you who are coming to the lab, you can do so. If you want to work remotely, is also fine. Okay, no problem. Okay, so thank you very much. Okay, and I will speak to you all again next week.